Then I'm gonna just mark down all of you who came today, and then I'll add a couple points of extra credit towards your overall course grade, which you probably won't see until the end of the course. That's when I'll adjust your grade. That's an easier way to do it. Okay, we'll get started. Well, I guess before I start talking about content, hopefully you saw my email I sent out today. So I am pretty sure that the Cengage situation is resolved. If you haven't tried already, if you want to take a couple of minutes right now to try to log in and see if you can access the material again. I totally apologize for that. From my understanding, I think they were able to fix it for the most part. It looks like all of the people with BiblioU, they ended up paying for the access. So you should have access. You shouldn't have to, at this point, pay for it. So if you have any comments, you can put them in the chat, or, obviously you can say them too, but hopefully that is working for you. I totally recognize that that is frustrating, that for a whole week you couldn't have access. So in light of that, as I mentioned, there were 13 quizzes that are required for this course. You will see that your first 2 quizzes I gave everyone 100% on. So hopefully that makes up for the fact that you cannot access it. So and because of that, for this week, I'm going to kind of discuss with the first 2 chapters, which are related to basic functions and components of energy and fossil fuels. I'm going to kind of run through that. And again, that's because your first 2 quizzes, now you can skip those. So let me look at what those are called, but you all have 100% on them. And then if you already made an attempt on those quizzes, I just automatically made your grade on them 100 to make it fair for the people who attempted them. So hopefully that sounds good to everyone. I'm just going to check and make sure that I know what those 2 were called. So
was it just chapter 1 and 2?
Correct. Yep, just chapter 1 and 2. So looking at your content, you can start on the next quiz, which should be, if you're going by the order of things, it should be part 2, fossil fuels, chapter 3. So your chapter 3 quiz is the next one you'll have to take. So you can skip the chapter 1 quiz that was on energy basics on that chapter, and you can skip the chapter 2 quiz that was on past, present, and future world energy use. You already have 100 on those. So start at part 2, fossil fuels, chapter 3. Hopefully that is fair to all of you. If you have any other concerns, please let me know. But also make sure that you're there. Or no, hopefully Cengage now is going to be smooth sailing for the rest. The other thing I wanted to know about Cengage for all of you, there are an option when you're going through the course material. There's something called a video discussion. You do not have to do those. So you can just totally skip those. They might show up as a grade book as a 0 or as a dash, but don't worry about it. It's not counted towards your final grade. So the only thing you have to worry about are the quizzes in Cengage. And if you want, if it makes it easier for you, I can write down for you the quiz numbers, because since some of the material is skipped, you might go from quiz 3 to quiz 5. So, okay, good question. And that's the other thing I wanted to talk about. So if you hadn't noticed, a significant portion of week 1 or of those first 2 quizzes was math. And I was shocked on that. So that is part of the reason too why I said, okay, we're not even gonna worry about that. So I think that the math is looking at like future weeks, it looks to be about half of the questions. So when you're taking the quiz, for example, for the next quiz you take, it looks like about the first half of the questions are like related to equations and formulas. The second half is like verbal, like qualitative questions. So I think going forward, if this is okay with all of you, I imagine that the math portion is the part that's going to be the most difficult. So in these meetings, I can start kind of going through like those, like the formulas and the equations, and go through the questions that are related to the math side of things, just so it's easier for all of you. And so this time is beneficial. So hopefully that makes sense. So, but yeah, so there does seem to be a significant amount of questions related, like numerical based questions. So I think too, this is the first time we've used Cengage for this course. So, you know, at the end of this, you know, please give me like your feedback on how I can do better, of course, but also how, like, if you don't like Cengage, if you think that like the questions weren't like testing your knowledge well or testing whatever, you know, let me know, give me the feedback you have. So I think it definitely will be helpful for courses to come. But okay, so for now, hopefully everyone is all set with Cengage. If you are not, please send me an email. Like I said, too, I will probably post like midterm grades in like 3-4 weeks, like just to kind of give you like a guideline for where you're at. So hopefully that is good too, but just make sure you're staying up on top of things. So, you know, there's 13 quizzes. So now there's only 11 quizzes you have to do, but make sure you're doing at least one a week, but you should really be doing 2 a week. Just, you know, to make sure you're staying on top of things. So yeah, that's the only thing you have to worry about is those quizzes. But okay, so I'm just gonna share my screen real fast here. Okay. Can you guys see my PowerPoint? I have a PowerPoint slide up right now.
Yeah, I can see it.
Yes.
Okay, perfect. So I'm not really going to go into like the formulas and stuff that the first 2 quizzes talk about, because I don't think it's the information that is going to be A, most interesting, and B, most relevant for the weeks to come. I think in order to master the math portion, you've got to understand where the numbers are coming from and what the words are meaning. So in light of this, I'm going to kind of just briefly run by introductory like concepts related to work, power, energy, fossil fuels. And so hopefully this will kind of give a head start into the next couple of weeks when we start talking about these different forms of alternative energy. So, and like I said, for next week, I will, my plan is to kind of talk about the math. Maybe I'll try to squeeze in enough like formula related stuff for like the next 3 quizzes. So just so you know that too. And I don't know if anyone's tried it yet, but please let me know if you do not have multiple attempts on the quizzes. I'm hoping you do, because that way, if you take a quiz before this course, you can kind of, you know, see, I can go over things and you can see what you did wrong and retake it. I'm hoping that's the case, but let me know if you can't retake the quizzes, and I will contact Cengage and see if that's an option, or I can probably give you like a reattempt on it, because I want you to at least have 2 attempts on the quizzes. But okay, so like I said, we're just gonna kind of briefly talk about these main concepts here. So I attached this diagram at the beginning. I'll pause or for a minute. If you want to take a minute to read it, go straight ahead, but I'll kind of work through it. And basically, I think this is a perfect description of these 3 terms. So work, energy, and power obviously are all terms you've heard before, but when talking about energy and the creation of energy, these 3 components are all very much related, which is difficult because that means it can be very much mixed up. So that's kind of why I wanted to show this a side by side of the difference between all of these. So I'm going to start in the middle. So energy, because we all, you know what energy is, but basically what energy is in like physics sense is it's the capacity for doing work. And when you see the word doing work, I'll go over to the left in a minute and talk about what work is. Basically what that means is the capacity to make change. So, and that makes sense if you think about it, because like anytime you use energy, you're changing something, right? But that's ultimately what energy is at the most basic sense. So the example they have here is, so like, you must have energy to accomplish work. So it's like the currency for performing work. So in order, before you can perform work, you need energy. So to do 100 joules of work, you must expend 100 joules of energy. And so this concept of joules, you might not have heard that term before, but basically that is just a unit for energy. And when I mean unit, I mean that's just how we are counting energy. So for example, the unit for speed is meters per second or miles per hour. So likewise, the unit for energy is just joules, which interesting enough, if you type in what are the units for joules, you will see that it's comprised of, I'm going to actually look at it because I don't know off the top of my head. So the unit for joules, I just looked it up, is kilogram times meters cubed over second squared. So 1 joule equals 1 kilogram times meters squared divided by second squared, which I know that makes absolutely no sense, but I think it was one of the formulas they talked about. But all that means is like joules is just a simplified way to write the unit for energy. So they took the words kilogram times meter squared divided by second squared and just were like, okay, that's too difficult to write. Like, let's just call it joules and call it good. So that's all that means. It's kind of like saying like miles per hour is, technically if we wrote it out the long way, it'd be miles divided by hours, but we just denote it as MPH, right? So it's kind of the same thing. But basically the only thing you need to know is that joules is just a unit that we use for energy, similar to how meters per second is a unit for speed, or how watts is a unit for power. So now going over to the left, so work. So we already know now that we need energy in order to do work. So work just refers to any activity that involves a force and movement in the direction of a force. So for example, here they have a force of 20 newtons, which is another unit. So newtons is a unit of force. Pushing an object 5 meters in the direction of the force does 100 joules of work, which if we go back to the right, you can see, okay, 100 joules of work means that we expended 100 joules of energy. So we're kind of seeing that there's like this relationship between all of them and a balancing act. So this last term on the right here, power. So power is a rate of doing work. So it's how quickly you're doing work, basically. So anytime you see the word rate, typically it means a unit divided by a unit. So power is the rate of work, which means it's work divided by time, right? So it's how quickly you're doing something. So if you do 100 joules of work in 1 second, you're using 100 joules of energy, but it also means that the power is 100 watts. And that's because 1 joule equals, in fact, I want to make sure I say this right. So sorry, I just wanted to double check myself. But so basically what this is saying, so if you do 100 joules of work in 1 second, you are having 100 watts. And that is kind of going back to the fact that watts is the same thing as saying joules per second. So this is kind of a concept that when they're talking about the math thing is difficult to understand. And I hope I'm not confusing you. And if I am, please stop me and I'll explain it better. But basically, sometimes in order to simplify units, they'll come up with a new word for it. Similar to how I said 1 joule is 1 kilogram times meter squared over a second squared. 1 watt is 1 joule over 1 second. So that's kind of just showing you that, like, even though watts and joules aren't like the same word, they are still very much related. And it's just the fact that watts is just telling you how many joules you're compelling over a given amount of seconds. So again, I hope that wasn't confusing to you, but basically just, that's just an example of the differences between all 3 of those and the relationship between all 3 of those. So hopefully you, at the very least, can see that work, energy, and power are all related in a lot of senses. But ultimately, the one that we're dealing with in this course and the one we're going to be talking about is the middle one, which is energy. So kind of moving on. So why is energy important? So we already talked about how energy is the capacity for doing work, or the ability to do work, or the, ability to create change. And so that's important because essentially we need to have energy to do anything, like literally, right? I mean, so when we think of something as basic as like on the molecular level and dealing with the human body, like breakdown and buildup of molecules, transporting molecules across membranes, all of this is important to energy. And also what's important to note here is that it cannot be recycled. So that's why we need a constant amount of energy, which for us is the food, is in the form of food, which we'll talk about this later on, but food is just chemical energy. So as you can see, that's kind of bringing up another point. So, and it's this idea, which you probably heard before, that is energy can't be created or destroyed. It can only transfer forms. So that is why energy is so important and so useful. And also it's a key thing to always, if you're going to remember anything from this course, it's that. And it's the fact that energy, how we're utilizing it in everyday form is we're not creating it. Like all of these different alternative energy forms that we're using, we're not creating energy. Because you can't create energy, you can't destroy it. But what we're doing is converting the form of energy or converting forms of energy to make it more valuable. So, like that's what this example is showing you. So this breakdown and buildup of molecules, transfer of molecules across membranes, all of that is talking about kinetic energy. So you've probably heard of the word kinetic energy, which is just energy in motion. So all of this is related. So, transferring chemical energy is allowing us to transfer it to kinetic energy, which allows us to move, and that's a very literal example, but that's just showing you that like all of these different forms of electricity are very, very valuable. And we're constantly transferring and creating, or not creating, but transferring to different forms of energy to make it more valuable for us. So another thing to note here, and it's the fact that energy in its secondary form is electricity. I'm going to talk about that in a minute here, but I think that is something that is always confusing to people. And it's this idea that energy and electricity, are they the same thing? Are they not? And it's confusing. But ultimately, we're going to talk about electrical energy in a minute here. But basically, electricity is the main thing that we are utilizing in modern day society. So that's ultimately, the most powerful tool we use. And all of that is related to this transfer of energy that we're going to talk about in a minute. So just to kind of briefly talk about some types of energy. So mechanical energy, I think there's mechanical energy is similar to kinetic energy. So I'm going to kind of, I'll leave that out for next time. But, thermal energy, we know that is something that gives off heat. So I'll think I have a diagram. Yep. Oh, did I skip a page? I'm so sorry, you guys, I skipped a page. We're gonna start here. Okay, so basic law of energy, I just stated that, but it's the fact that it can't be created or formed or destroyed. It just changes forms. So, and this is called the first law of thermodynamics. So in the first chapter, they talk about thermodynamics a lot. So I've written here the 3 laws of thermodynamics, which we're kind of going to briefly cover. First one, what I just said, so the total energy of the universe is constant. It makes sense with the basic law of energy, right? It can't be created or formed, only changes forms. So you don't really have to understand this equation, but basically all it's saying is that the energy in the system equals the energy in the surroundings. And so really that's the change is the same ultimately. That's what this triangle, if you ever see this triangle, it just means the change. The second law is something called the entropy. So the total entropy of the universe is always increasing. So I, as an engineer and as a scientist, I love the concept of entropy. I think it's really, really interesting. And, if you're interested on it, I think there's a lot of really interesting studies and things related to entropy, but it is a very confusing concept to understand. I'm going to explain it in the most simplest sense, but please, if it's confusing, stop me, or if you have any questions, let me know. But basically what entropy is it's the degree of disorder, okay? So on this right here, you can see that I have kind of a picture of these circles. We'll just pretend those are atoms. And on the leftmost side, we can see that they're highly random. They're in various spots. It's way more disordered than all the way to the right, when they're all in a ball and all composed together. So what this idea of entropy is saying is that entropy in the universe is always increasing. So as time goes on, the universe is just constantly becoming more entropic. And the reason for that, and if we think about it, like as us humans, the reason that entropy is always increasing, it's because changes are more likely than no changes, right? Like everything you do, you're constantly creating entropy. Every time you breathe, you're breathing molecules of oxygen, or you're breathing molecules of carbon dioxide or whatever into the air. Anytime you do anything, you knock over a glass, like you do any movement, everything's creating entropy. So that's kind of why we talk about it. So the likelihood of change or the likelihood of something happen is way more likely than nothing, right? And that's kind of, if you look at a lot of like the Big Bang Theory, like talking on a huge picture here, like it all boils down to that concept and the fact that like entropy or this degree of disorder, it's always more likely. So that's why entropy is always increasing. So just things are more likely to happen than nothing to happen. So I think it's really interesting, at least, but I know it's a difficult concept to understand. But for now, this is all I'm going to cover on it. So the other thing I have on the right there is kind of related back to that first law. We're not really going to talk about the third law at all. In fact, in all my years of school, I have very seldom knowledge and very seldom been taught much on the third law there. But basically what she says is entropy of a pure, perfectly formed crystal substance at absolute zero, which is the temperature, is zero. But that it doesn't really apply to energy or anything. So we really just focus on the first two laws. But the first law is the one that we're really, really focusing on for this course. But I just wanted to provide a brief overview of the second one because I think it's interesting. But so back to the first law, this picture of this cow on the right here. So is a perfect example of transfer of energy and the fact that it's never being created or destroyed. So I think that like a lot of people are confused by the fact that, well, if I am walking and I'm having kinetic energy and I stop walking, that's destroying energy, but it's never destroying energy. You're just always transferring forms of energy. You just might not always be able to visualize it. So this is kind of what it's showing you. So in this example, they're inputting or they're eating 100% of their energy, but then they are losing 25% that's going to be stored in their tissue. Another 25% is going to get lost as respiration. So when you're breathing, another percent is going to get lost in the form of heat, right? We know that after we run, we get really, really tired and hot, and it's because we're transferring energy from kinetic to thermal. And then we know at the end there, loss is in the form of excretion or waste. So yeah, I think that's a perfect example that's showing you that energy is never, ever getting created or destroyed. It's just constantly changing into all these different forms, into different forms that you might not see. So I think that's, why it's such a difficult concept for a lot of people to grasp. But hopefully that visualization helped, and hopefully this visualization of the idea of entropy helped too. But really for now, I think for this class, at least, the only thing you need to know about entropy is just the degree of disorder. However in depth you want to learn about that, go for it, because it's interesting. But yeah. Okay, so kind of back to this, which I showed in a minute. So, there's just a lot of different types of energy, chemical energy, which I briefly touched on a minute ago when I talked about food, electromagnetic energy, ionization energy, nuclear energy, thermal energy. There's all of these different forms of energy that constantly we can change forms of one energy to the next, which is why when talking about alternative energy, it's endless, and why I think it's such a great thing to major in and a great thing to gain knowledge on. And it's because of this diagram. There's a million different types of energies. Really, I mean, I think all of them, there's subsets of kinetic energy, and there's kinetic potential energy, everything like that. So it's just valuable to know that the fact that there's so many different types of energies out in the universe make it almost endless opportunities for us to figure out ways to utilize them, to create them, or to form them into something that's more useful and beneficial for society. And that's kind of what this next diagram is showing you. So electrical energy, the reason that I have this kind of bolded here is that is probably the most significant form of energy that, in my opinion, that is utilized. So, right, electrical energy is ultimately caused by the moving of electric charges. So the amount of energy depends on obviously the speed of the charges. So the faster they're moved, the more electrical energy is carried. Electrical energy, I think of like a circuit. We have, I don't know all of your experiences in electricity, but electricity basically is the flow of electrons through a circuit. All of that is related back to electrical energy. And we know how useful electricity is in modern day society. So it does a lot. So that's kind of why I think a lot of the forms of energy that we are transferring or changing forms of is we are ultimately converting it to electrical energy, since that is something that is very useful to harness. So in these four examples here, and I have a link at the bottom here if you want to look at more, these are just kind of showing you different ways that we're transferring energy. And again, note I didn't say creating energy, we're transferring it. We're transferring it into forms that are going to be more useful for us. So in the first example, nuclear power plant. So nuclear energy heats water into a steam. The steam is used to turn a turbine, which fires up a generator to give electric charges their energy. So in that example alone, there's a couple things I want you to know. So one, the first sentence there, nuclear energy heats water into steam, heats, thermal energy, right? The steam is used to turn a turbine blade, mechanical energy, which fires up a generator to give electric charges their energy, electrical energy. So, at the most basic forms of understanding how we're harnessing and utilizing energy and electricity, it's the fact that we're taking forms that are readily available and easy to harness, and we're converting them into forms that are useful for us, like electrical energy. Second example there, so a hydroelectric plant. So we have falling water is used to spin turbines. So in there, falling water, you're like, okay, well, what the heck's being used there, right? Well, falling water is gravitational energy, right? If we go back to this, that's a form of energy or potential energy you can think about. So this potential energy is falling, that water is used to spin a turbine blade. So then our potential energy or gravitational energy is turning into mechanical energy. Then the blades turn the generator, which the generator creates electrical energy. So another example of how we're just constantly converting different forms multiple times in these scenarios to ultimately create electrical energy. Windmills, an easy one, right? So wind power turns the turbine blades, which, makes the generator create electrical energy. And then solar energy is the only one that's a little bit different, right? It's not really using a mechanical form there. Basically, solar energy is produced directly from the sun. So it's converted into electricity and used to heat, air, water, and other fluids. And we'll talk about that one more when it comes. But ultimately, the idea here is I just wanted to show a visualization of like all of these different forms of energy. So going forward in the class, we're going to spend a lot of time talking about wind energy and solar energy, but at least this kind of gives an overview for like how and why it's actually working. Okay, so I just showed all those different forms of energy, but obviously for us, we don't use all of them, and we don't use them all the same amount or the same sources, I guess. So this on the right here, it's a little blurry, but I thought it was interesting. I just I took a snapshot of it, but I have the reference in here if you ever want to, look at it more in depth. But basically, it's just showing you that still to this day, a large majority of our energy is created by fossil fuels and the burning of fossil fuels. So that is natural gas and coal, which I talked about fossil fuels a little bit briefly last week about how fossil fuels are just hydrocarbons. I talked about why hydrocarbons are bad for the environment, right? Because the burning of them, which is how we're creating energy, is combusting those hydrocarbons. And then we have carbon molecules that are just readily in the air that easily bond with the oxygen in the air. CO2 is what we don't want, and that's what's created. So coal and natural gas and oil are all forms of hydrocarbons. And still to this day, you can see in this diagram is showing about 60% coal, 19, natural gas 40 is, so 60% of all of our electricity generation is created from those sources. Nuclear is about 20, renewables, which is including all the different forms we're talking about in this course, solar energy, wind energy, hydroelectric energy is only accounting for 20%. And obviously the goal by looking at this. Oh, they have it here. It's a blurry, but like wind is 4.4%, hydro 7.3, solar 2.3. But basically the goal, in the future is to increase that green, right? We want more renewable energies, and that's because things like coal and natural gas are non-renewable. So we're not going to have them around forever. So that's the point of this course, to talk about the renewables and talk about the benefits of them, but also talk about, why is there that gap? There's a reason that we're not just using 1 million solar panels and powering the world. There's a reason that we don't have every single car is an electric car right now. So yeah, we'll talk about all that, but hopefully that's a brief overview. So the only thing I wanted to mention here is I think is important. So another gap that I think a lot of society has is, well, how are we creating energy with coal? At least that for me, like that was always something like they just always say it, right? Like we know coal is bad, we know it's a fossil fuel, we know it creates CO2, but like again, like I just never felt like anyone told me why. So that's why I wanted to point it out here. So fossil fuel plants basically burn those hydrocarbons, and that's used to generate steam, which moves turbines, which creates electricity. So it's almost a similar form to all of the ones we talked about here, right? It's the same concept of renewable energy. We're transferring the forms of energy into something that's more useful, electrical energy, which creates electricity. In this case, why hydrocarbons are used is because ultimately they have a lot of they harness a lot of energy inside of them, which we can talk more about that, or I can provide some resources if you're interested as to why. But so they carry a lot of, I guess, potential energy or chemical energy. I'm not exactly sure which one is proper to say there, but they carry a lot of it. So that's kind of why we're burning it or utilizing it. So we're utilizing that energy inside of those hydrocarbons to create thermal energy, which is burning it, which creates kinetic energy, which creates electrical energy, which creates ultimately electricity. So yeah, those are just some of the references I used, but hopefully that was at least somewhat informative. Like I said, I just wanted to provide a brief overview of the first 2 chapters, at least what I wanted you to take out of it. I think there was way more content in those 2 chapters than is probably needed. So that's why also I think giving you guys both the passes on those first 2 quizzes is important. But for now, I know I ended a little bit early, so if you have any questions at all, feel free to ask those right now. But if not, you're free to head out. I'll see you next week. And like I said, I'll probably talk more about the math related concepts for the next couple of quizzes. Since it's only a 7-week course and we have 13 or 11 quizzes now to get through, I'll probably have to kind of move a lot quicker, at a quicker pace, but hopefully we'll at least save time to kind of talk through it like this too, because I think it's helpful to talk about visualizations of things instead of just talking about the boring math stuff, right? So yeah, any questions at all or anything? But if not, you're free to go.
No. No, I think I'm good.
You're good? Okay, well, great. Just let me know if you make sure you guys can all access Cengage tonight. Make sure, send me an email if there's any questions. I try to get back at least within the day or 2.
Alrighty.
Have a nice night.